Okay, hello everybody. Welcome to this seminar session of our Thursdays at BrIAS. So today we have two very interesting talks, and I'm very happy to introduce the first one. Our first speaker is Professor Andrea Roli from the University of Bologna. So Andrea is someone who's very well known here in various departments at ULB, as he's often visiting us. He has also visited us as a fellow of the BrIAS multiple times. We're very happy to have him here. So actually this is his second talk this year, and we are actually also expecting a third one because Andrea, beside being an excellent scientist who works on swarm robotics and stuff around it, is also a musician, and he promised us also to give us a seminar and maybe a little concert in the future. So I'm just saying this to seal the deal in front of the cameras. And so you are all witness. We will also want to listen to him playing his tiorba or his Baroque guitar. We will see what. So we leave you the choice of the instrument at least. This said, without further ado, I am pleased to leave him the stage, so that's yours.
Thanks, Emanuele, for this nice and bizarre introduction, because now I cannot avoid to plan another talk on that subject. But for today, thanks for being here, and the subject of today's talk will be, let's say, slightly more scientific than Baroque music and complex systems. When I thought about the subject of this talk, I considered that the audience comes from different backgrounds. And I realized that there is a fil rouge in my research since I think about 30 years, that is dynamical criticality. In several parts of the activities of research I've done, I've focused on dynamical properties of the systems from the perspective of a computer scientist. So when computation can be translated into the dynamics of a system. And in particular, there are complex systems that exhibit properties that are very useful for computation. The personal motivation for this subject comes from two books that I read actually when I was still a student. The Origins of Order by Stuart Kauffman, a book I think fundamental for self-organization and evolution in living systems in nature, but also with models that can be studied and applied in computer science. And the book by Roberto Serra and Gianni Zanarini, Complex Systems and Cognitive Processes, that connects beautifully the properties of dynamical systems with the ones of computational systems. These books are from early 90s, but I think they are still now important to describe these subjects. So briefly, the outline of what I'm going to talk about is that we often observe that some complex systems in nature, and so natural or artificial, exhibit some properties, and they are typically poised, so living at the edge between order and disorder. And these systems have this particular dynamical regime that makes it possible for them to achieve an optimal trade-off between flexibility and robustness. And this is something that we very often aim at in designing artificial systems, but also it's a property that we observe in natural living systems. And in this, criticality may play the role of a general principle that can be used both to study and to design systems. I will start with a little bit of background, rather informally. So I apologize in advance for the physicists here, expert in statistical physics. I will be really informal in this introduction. The term criticality has its roots in the theory of phase transitions. We are all familiar with the phenomena of phase transitions in nature, for example, a transition of water from liquid to gas operated by tuning a specific control parameter, which is the temperature, or other general properties like being ferromagnetic or paramagnetic of iron. And in this case, this change is tuned by changing the temperature. But the point is that in all these situations, we can find a so-called order parameter, which is in the model a parameter that undergoes an abrupt change directly or in one of its derivatives. And this is called phase transition. So the point is that we are interested in the phenomena that are called critical, that corresponds to the critical values of the control parameter that produces this abrupt change in the order parameter. But we are especially interested, or actually I am especially interested in what are often called second order phase transitions, which are the ones in which the system shows different behaviors in the two conditions that are separated by this critical surface. So we do not just observe properties that change, but typical behaviors that change. So the bouquet of behaviors that the system exhibits changes in the two sides of this critical line. And very interesting properties, I would say probably the more interesting properties lie there in the critical separation between these two regimes, these two conditions. I'll briefly give you a couple of examples. The first one is the Ising model, which is rather known, and the second one will take a few minutes more than the explanation of the Ising model. It is the one connected to Boolean networks, which are also will be used also in a later part of my talk. So the Ising model can be simply described as a lattice of cells, atoms, that can have two spins, quantified in plus or minus 1, and the system has a function, a general function that is an energy that is given by the summation of the product of the adjacent cells, of the spins of the adjacent cells. So we can see that if spins are aligned, so they have the same sign, then there is a negative contribution to the energy. And guess we would like to look for the minimum energy conditions of the system. If we simulate the system with a Monte Carlo method, then we can apply a simple probabilistic rule for the flip of the spins using a Boltzmann probability, which depends on the difference in the total energy that a possible flip may introduce in the system, and depends on a control parameter, which is called temperature here. Roughly speaking, if the temperature is low, only, or let's say the most probable flips accepted are the ones that produces a decrease in the global energy, while if the temperature is high, then the system may accept also flips in the spins that do not produce a decrease in the energy, so it may also increase it. And in this system, we have an order parameter, so we look at properties of the magnetization, which is just the average value of the spins. In this rather simple description, we can find interesting properties and a phase transition. That, of course, depends on the parameters k and j of the energy function. But here, to keep things simple, let's consider that we have low temperature, and in that case, spins tend to be aligned. And this alignment tendency spreads across all the system. So we may have almost all the spins at -1 or almost all at 1. While the temperature increases, this property is slightly perturbed, and we have then a phase transition that divides this behavior of let's say, ordered possibilities, either all, almost all, +1 or -1, to the disordered regime in which the temperature is such that basically all the spin flips are accepted, and so we have a constant oscillations of all the spins. We have complete random behavior of the system. But the point is that this transition is abrupt, and the larger the system, or the system goes to infinity, it is possible to prove that there is a discontinuous moment at the very critical value of the parameter of the temperature. So this shows in a simple system that depending on a parameter, there is an abrupt transition between a condition in which the system can be in an ordered situation, either all +1 or -1, and it is also a stable condition. And the second regime is a completely random one. So here, basically, every spin have the same probability of being +1 or -1, and it continues to oscillate. Here you see a plot taken from a picture of a nice book on phase transitions by Ricard Solé, in which these points are plotted by a simulation of the system, and you see this clear behavior. But there is another system very rich in terms of dynamics that exhibit a phase transition between order and disorder, and this is called Boolean networks, which have been introduced by Kaufman 55 years ago, almost 57. I don't know if it was January, February, or June, actually, but the paper was in the first paper was in '69. And they were introduced, and they are discussed also in the book that I mentioned at the beginning of the talk, but they were introduced earlier as a model, a generic model for genetic networks. It is a typical case of a system with discrete states that evolve in time in discrete steps. So it's rather easy to study in theory, then it's much more difficult for simulations if we have large systems. The idea is that we have a graph composed of nodes associated to a Boolean value, which represents the state of the node, and a Boolean function, which is used to update the value of this node. The inputs of the functions come from the values of the node that are connected with an incoming arrow to the incumbent node, the node that we are considering. And this defines somehow the structure of the network, while we have to decide also what is the dynamics of the network. So what are the rules that we can apply to evolve in time the network? Here, and for the rest of the talk, I will consider probably the easiest way for updating this system that consists in apply synchronously the update function of each node. So at the very same moment, we update the values of each node of the network by applying the Boolean function. So we read the values of the inputs and we update the state of the system synchronously and applying all the functions, all the Boolean functions in a deterministic way. So in this case, we have a system composed of, if the network is composed of n nodes, we have 2 to the power of n possible states for the system, so all the possible combinations of a Boolean vector of length n. And in principle, we could study the transitions and the dynamics of the system. Consider that we have one successor per each state, per each system state, because the functions are applied synchronously and are deterministic. And we have a finite number of states. So for small systems, no surprise can come. Okay, we could exhaustively explore the state space and know everything about the dynamics of the system. In fact, we could, for this simple network, this is a really a toy model. We can have 3 nodes, and we have for each node a truth table saying what is the possible value. So for x1, we see what is its future state depending on this truth table, and the same for the other two nodes. But the point that is of interest is that if we run this network starting from an initial state, given the properties of the dynamics, we can subdivide the trajectories in the state space in a transient, so a sequence of nodes ending to, and let's say, landing to an attractor, which might be a fixed point, so the system doesn't move any longer from a specific state, or a cycle, and the system just goes on forever, repeatedly on this cycle of states. This, for example, is the complete state space of the network that I've shown you in the picture before. We have two fixed points and a cycle of length 2. No surprise at all. So this model can be used, for example, to try to match properties of real cells. We extract some information about genes, and we can create a model, a specific model of that specific that specific cell in given properties. But what is particularly interest for me now is a specific model of Boolean networks that is called random Boolean network. And it's this model that exhibits a phase transition that is of particular interest. Let's consider a random Boolean network of n nodes with exactly k inputs per node. This hypothesis can be relaxed, but take it like this because it's easier to explain it. And for each node, we choose k inputs, so k values for the Boolean functions, k inputs for the Boolean function at random from the other nodes of the network. And then we define the function, the Boolean functions, by completing a truth table like this, putting a 1 with probability 0.5. So basically, we flip a coin, a fair coin, and we assign 0 or 1 depending on the outcome of this coin. And we decide what are the Boolean functions. Now, in this, I would say, probably incomprehensible and we could think meaningless ensemble of nodes with Boolean functions that are chosen at random and connections that are random, some interesting order emerges. So let's suppose that we tune k. We can have the number of inputs per each node, 1, 2, 3, 4, 5, etc. If k is equal to 1, it means that every node has exactly one input, so the Boolean functions simply manipulate one input. We have very few options for that. And in fact, what we have is a very ordered dynamics. Here you see the picture, the graph representing the state space of a random Boolean network of 10 nodes. So we have 1,024 possible states for the system. We see that we have just a couple of fixed points and a very ordered way for reaching the attractors. So funnels that define paths to the fixed point, which are really rather rigid. And in fact, these systems have a very frozen dynamics. So if we perturb a state or a node of the system, then the perturbation dies out quickly, and the system settles down again to the same attractor. So it is also robust. And it might work, for example, as a good system for classifying for specific classes, very few classes. It can absorb, it can take as an input the initial state and then go toward a fixed point representing the class of the system. And if we perturb this, this initial state, the network is very likely to go again to the same attractor. But it's a rather poor dynamics. Now let's try, for example, with values of k equal to 3 or greater than 3. I wonder why I didn't choose 2 now, but let's hold it. Or probably you are wondering why. And in this case, we have what is called pseudo-chaos we have a finite system, it cannot be called chaos, but we informally say that we have a chaotic condition in which we have very long cycles. So let's consider Boolean networks of size 100, and 2 to the power of n is for us something that has no limit. Is not possible, of course, to make all the steps of an attractor of more or less this length. So for us, it's something without a conclusion. It's not a system that goes towards a meaningful attractor. And it presents the properties that are typical of deterministic chaos for the ones of you who are familiar with it. If we start with an initial condition and we slightly perturb the initial condition, the two trajectories diverge very quickly, exponentially. So we cannot contain the distance between the two trajectories, and just a slight modification of the initial condition produces enormous differences in the dynamics of the system. And it is also not robust at all. So if we are in an attractor and we perturb it, it's very likely that the system goes to another attractor. So for us, it's nothing that reacts in a robust way to the perturbation of the system. No surprise that for k equal to 2, we have a phase transition, and we have exactly the criticality condition, in which the system exhibits a kind of mixture of properties of order and disorder. We have cycles that are usually quite high in number. They are not very long, so they can be executed and represent categories of the behavior of the network. They are robust, so small perturbation does not affect the steady state behavior of the network. Some perturbations can make the network jumping from an attractor to another one, so there are transitions that are allowed. And so in this mixture, we have richer dynamics than ordered networks, but much more stable dynamics with respect to the chaotic networks. And it can be proven in theory with statistical physics methods that there is indeed a phase transition, and we have actually two order parameters, two control parameters. We have k, but we have also p, the probability of assigning a 1 into the truth table. And in fact, by tuning k and p, we can decide whether to leave or to generate networks from an ensemble that characterizes ordered networks or chaotic ones with a rather high value of k and a value of p, so the probability of having 1 that is around 0.5. That means we have much more variability and possibilities in the Boolean functions. But there is a separation. This is a line, a critical line that separates the two regimes. And in fact, with very large systems, we can observe these properties. And now you have to be precise. We usually talk about the edge of chaos for these phenomena, so the systems that are poised between order and disorder. And it is common to say disorder, chaos, randomness interchangeably. Actually, there is a difference. Disorder regimes can be random. That means that there is no structure at all in the dynamics of the system. They can be chaotic in the sense of deterministic chaos. And in that case, there is a structure. But unfortunately, we cannot make predictions for these systems because they are they exhibit sensitivity with respect to initial conditions. But still, what is of interest to us is that we have a separation between order and disorder regimes. More about that, especially when we study finite systems or living systems or finite systems, these transitions are not as sharp as we can find in statistical physics model. We have point lines or surfaces of representing the critical values for the parameters. But in real life, we have extended critical situations. So we have a range of values, we have a range of behaviors that are exactly a new condition between order and disorder. And it's also important to observe the fact that while in models we have a sharp transition, so a discontinuity in some function, in the real world we have just sharp changes, but not as abrupt as in discontinuous function. So we can somehow live in a critical extended region and find there a place where the dynamics of interest can take place. There are also some interesting properties of systems living between order and disorder. The first one is that if we perturb a system that is critical, usually transient to go back to an attractor, so to a steady state, are rather long. This can be good or bad depending on what we want to use the system for. But in general, this means that there is a computation involving several parts of the system. So this is also linked to the fact that we have long-range correlations between elements of the system. This means that if we take a random Boolean net that is critical or the Ising model in a critical condition, we can find statistical correlations between elements that are far away. That means that information is spread across the system. And another important property that I just mentioned, because it's a very large subject, is connected to scale-free properties. Scale-free properties are the ones represented by power law functions and they are typical of many phenomena that are associated to criticality. The essence of that is that there is not a particular scale at which we can observe a phenomenon, but the phenomenon extends over all the possible scales of the system. So this means that we cannot do averages, for example. Now, what is the criticality, the importance of criticality? Well, I would say since the early 80s, the idea that critical system can behave in an interesting way and deserve to be studied was already present in the studies in complex systems. And the idea is that a critical system can attain the best balance between robustness and adaptivity. And this is something that we look for in artificial systems, for example. And they can be reliable in responding to the perturbation, to the inputs, while providing a large set of possible answers. So I can have a very stable system that answers always the same answer, that gives only or two answers. Okay, that's it. It is stable, okay, but the repertoire of possibilities of the system is really limited. On the other hand, I can have a system that reacts differently from any input, and this is useless because it doesn't provide information to me. But a system that is able to classify the inputs robustly, but still with wide possibility for discrimination, is really an important property. So we usually look for systems with these properties. And observing that this is possible for critical systems make criticality a good candidate for a design principle. There are indeed two versions of the criticality hypothesis. One is connected to evolution, so the possibility of evolving systems, and it's the reason why it is said that living systems are critical, because they are subject to this kind of evolution, and critical systems, it has been proven, evolve better than ordered or disordered ones. But also a kind of behavioral version of this hypothesis that is connected to the capability of using information, so transformating, storing, and sending information and elaborating information in the system. And there have been results in both the sides that I've just quickly mentioned to go then to the results that are more related to my research. There are now, I think, thousands, hundreds, let's say, of papers showing that cells are critical, but not just cells. The brain is critical. There are very interesting results about that. also experimental. And also swarms, ants or birds, show critical behavior in their swarming. So it seems a property that can be generalized across living systems. But also for artificial systems, it seems that being critical is helpful. There are several examples of artificial neural nets that, when poised at criticality, perform better than the other ones. There are examples in reservoir computing, which is currently a very used technique. And in this case, it has been proven that critical Boolean nets perform better than the others if used as a reservoir. And analogous results were also found in local search for optimization. So in this general topic, in this subject that is really wide, from physics to biology to computer science, I made my personal investigations that I'm not going to detail to you today, but I will go to the last one that has to do with robotics and adaptive robotics, and it is, I think, more connected to the activities of BrIAS. But before that, let me mention three important questions that I had in mind when I basically started these research activities in criticality. And some have already, I would say, a partial answer. Some are still to be investigated more. So the first one is, does it always pay off to be critical? Do you find critical systems wherever, as it was in the 80s when deterministic chaos was found, or scale-free networks? Then everything is a scale-free. Now everything is critical. Well, when there is a question mark, often the answer is it depends, and in fact this is the case. Can robotics take advantage of criticality? This is the subject I will talk about, and then I will conclude with some considerations about the implications of criticality for the evolution of the biosphere and the society and all of us. So in general, from results I have achieved and also some other researchers, we cannot say that it is always good to be critical. There are conditions for which a system has an advantage of being critical. The main reason is that being critical is a cost. We need some redundancy, we need some flexibility, so the system cannot be really minimal, should be large enough. Computation is slightly longer than being completely ordered, and so it is not always the case that it is an advantage. So in general, the task should not be trivial, should not just ask for a couple of answers and that's it. It is usually a dynamic task that induces criticality. There is noise, there is uncertainty, and also if a system has to interact with an environment that is critical itself, then it means that it challenges more the system, and so the reactions should be somehow elaborated with care, and criticality pays off in this case. But this is just to answer the first question. Let's move to the second one, and that has to do with adaptive robots. So the idea is to use systems that can be poised at criticality and compare these systems with order and disorder behaviors, disorder regimes, by using these systems to control robots in an online adaptation context. When I say this, I basically refer to a condition that is in other fields called lifelong learning. So we have a system, in this case a robot, that has to adapt some of its parameters, or some of its structural definitions, in order to improve its performance with respect to a given metric. And this has to happen over the course of its activity. So there are not clear training phases and then phases in which the robot is is just making its stuff in the environment, but it has to be able to continuously learning what is better to improve the objective function of its performance metric. And I've of course used the Boolean networks to control robots. Of course, is because you clearly understand that I'm a fan of Boolean nets and I work on them, so I've used them. I'm not pretending that it was a choice extremely grounded in many scientific considerations. I like Boolean nets, I know how to use them, and so I made these tests. But there are many other ways to control robots, of course. Here we have a Boolean networks, and we have to couple it to the environment in order to control the robot. So we take values from the sensors that are somehow translated into values, Boolean values, that are used to override the values of some nodes of the network. Let's call them input nodes. The values, the Boolean values of some other nodes are taken and then converted to send signals to the actuators. So basically it's something similar to the use of classical artificial neural nets to control robots. The difference here is that we have a different domain for the values and different dynamics with respect to usual artificial neural nets. And somehow some advantages, because it's the level of abstraction is slightly higher, but also some disadvantages because we have to do with Boolean values all the time. So we have to translate values from sensors and translate values to send signals to the actuators. And this is the way we can couple a Boolean net to the robot and let the robot do actions in the world and perceive values from the world through sensors. What we can adapt of a Boolean net? Well, the Boolean functions, the links between the nodes, but you can also change these connections. These are not pre-stated, so we can do basically whatever we want in the coupling and in the structure of the network. There is a difference, though. The first two levels directly change or might change the dynamical regime of the network. If I change the Boolean functions or the connections, then the dynamical regime of the network is very likely to change. If I only change these connections and let the network untouched, I do not perturb the isolated characteristic dynamics of this network. What I just change is its behavior when it is immersed in a system, in an environment. I will show you results across all these, almost all these possibilities, but first I will focus on the last two. So we just keep the network as it is, and we try to adapt the connections, which seems really full, because I take something that I will show you is random Boolean nets of 100 nodes, of 1,000 nodes, random, critical, ordered, or chaotic, and then I just try to couple it to sensors and actuators, hoping that its dynamics will let the robot do what I want. I was surprised to observe results, but I don't think it's really silly, because actually what we are doing is that one. We have basically we have a dynamical system that could be rich in its dynamics, and we try to find the proper interactions with the system such that its dynamics has the properties that we are aiming at. So we are not touching directly the system, but we try to perturb it and read its reactions and reinterpret its reactions in such a way that the system behaves or exploits some of its dynamics in the direction that we want to go. So a simple idea is that we can, for example, change the connections from sensors to actuators, to the nodes of the network, leaving the nodes controlling the actuators fixed. So we have already a limitation, and now we limit further the possibilities. We just try to connect sensors to nodes of the network. And let's do things really simple. What is the mechanism for adapting? Well, the easiest mechanism that was introduced in cybernetics: try a configuration, evaluate it, modify slightly this configuration, evaluate it. If the modification is better or equal, keep it. Otherwise, throw it away and try another configuration from the initial one. A classical trial and test. We have no heuristics here to use, or, well, actually, in general, I suppose we don't have them. So I've chosen the easiest mechanism for adapting and the most limited way for coupling the environment to the network. The first test was a simple task. We wanted the robot be able to walk or to move as fast as possible in the arena, staying away from the obstacles. And of course, the goal was to test what is the performance among the different regimes of the network. So we have taken networks from the ordered regime. Given the similarity of the symmetry of this curve, we had to take different values for that, but always in the order. Chaotic is in the center, only one is enough, and critical on the two extremes of the line. And we tested networks with 100 and 1,000 nodes. The results, I give you only the summary. Of course, details are in the papers, or I can answer if you have specific questions. Surprisingly, I would say it was not that difficult to find networks enabling the robot to perform properly the task. The best ones were critical, and especially the larger networks, so 1,000 nodes, which is a blob of dynamics, was actually clearly better than ordered and chaotic ones. And this is just a comment, but it's really interesting. The worst ones were the ordered networks. Too frozen, too stiff, no way to move them. Chaotic networks were not performing as good as critical ones, but still not really bad. And this may be a suggestion. If I have a chaotic system, maybe I just need to add constraints to it in such a way it performs rather well or enough for our purposes. And it is better to start from a variety of behaviors with respect to starting from something that cannot provide itself behaviors. But of course, the best ones are critical, that are a mixture of these dynamics. But of course, collision avoidance with controlling only the links from sensors to nodes of the network are not enough. So with collaborators, we made experiments involving also other two tasks, so collision, but also area avoidance. So the robot should also detect the color of the floor and choose the proper one in which they have to stay, and moving objects from a side to another one, avoiding obstacles. And we tested different ways, different mechanisms for adapting the networks. So we can change both the connections from sensors to nodes and from nodes to actuators. We can change the Boolean functions only, so just touch, leave untouched the connections, but change the very dynamic of the network by perturbing the Boolean functions, or combine these two. Just a summary of results. overall critical networks were always performing better than the other ones. Here in this case, you see that chaotic do not perform well, do not perform as good as in the previous example. Here we have ordered networks that perform that are ranked second. But there are some notable outcomes. The first one is that the best results were achieved by using the mechanism of changing the connections between sensors and network and actuators, plus a little bit of changing the Boolean functions. If we add the fact that Boolean functions can be changed, we can observe that the criticality of the network, if taken as an isolated system, is somehow increased. So if we start from an ordered or a chaotic network and we change the Boolean functions during the adaptive process, these two seems to go or to tend towards a critical regime. So it means that also the adaptive process, reminding very loosely an artificial evolution context, are driving the network towards criticality, because the task is not easy. There is noise in the sensors and in the actuators, so there are elements favoring the arising of criticality. And also these results were confirmed by overimposing noise on the very dynamic of the network. So we perturbed randomly the values of the nodes of the network, not just sensors and actuators, but noise in the controller. And here, criticality was even better than in the other cases. So why this should work? The intuition is that critical systems provide a richer repertoire of dynamics with respect to the other two. And my view is that in this way, by changing the connections of the systems with the environment, we are basically shaping its dynamics. Like sculptures, we have there the material, the matter, and by adapting the connections, we are shaping this material in such a way that the shape is what we aim at. We actually shape the landscape of attractors of this of the system by exploiting the attractors that it naturally provides. So we have available already a very large set of possibilities, and we just have to find a way to couple this with the environment. And of course, this is another piece of evidence that in evolutionary or adaptive contexts, when the task requires it, the system is somehow biased towards criticality. There's a lot of work to do in the future, especially by testing more complex adaptive processes, because we want to have robust and adaptive robots, not just examples in simulations. And also, we are not forced to use always Boolean nets with pros and cons, but we can try other controllers, provided that we can assess their dynamical regime, so we can say whether they are critical or not. Now let's go to the conclusion and the final considerations about the implications of criticality that go to beyond the experiments in robotics. What we have observed is that if we have systems that have repeated interactions and they can change something of themselves, so if we have adaptive or systems in an evolutionary context, when they interact, they usually tend to go towards criticality. So it is very likely that if we apply some analysis technique of dynamical regimes to any level of the biosphere, we find critical conditions. And so we have to think about the biosphere as a nested hierarchy of critical systems from cells to ecosystems. And the same holds for the society, which is a living system not produced by simply by natural laws, but also by conventions and norms that we humans introduce. So we have a big responsibility here, because we are not doing with rigid systems that are there unperturbed. Luckily, they are not chaotic and completely disordered, otherwise we wouldn't be able to do anything. But they are critical. So we have to be responsible in our actions, in our act, because there are some consequences. First of all, there are long-range interactions. If I touch a system in an ecosystem here, it can have an effect on in time, maybe in long time, but an effect to another system. It is nothing to do with the butterfly effect. It is really a stable influence between elements that are distant in the system. If we apply a perturbation, we do not expect a reaction immediately, as in disorder or chaotic systems. The reaction might happen lately. And so if we act in the society or in the ecosystem, we don't have to expect immediately an answer or a reaction. Sometimes after a perturbation, if the system is critical, then after a transient, it goes to another attractor, different from the initial one, but not that different. So there might be mild differences in the new steady state conditions. And this can be a good way to analyze the reaction of the system, or a good way for slightly changing the dynamics of the system. And the other point, I go to the last one, if we want to move a system from its conditions, maybe it is too rigid or too chaotic, and we might try to inject some criticality in it in such a way that we can move it and adapt or condition its dynamics. But on the other hand, we have to be aware of the fact that we live in a critical world. And so the actions that we take have an effect, a long-term effect, on other parts of the systems and on other levels of the system. And I think this is especially important for the ones who work in technology, robotics, but also has to do with the environment. Just an example of application of criticality in soil restoration. Have a look at the TED talk given by Stuart Kaufman. At the end of the talk, he mentions a case in which by using fungal bacteria's community evolved naturally in compost, it is possible to restore the parts of the environment. So I leave you this. And I have to thank many people for the research that I've done so far, and also the results that I presented to you. Here, some in a given order. But also, I'd like to thank all the people at BrIAS, and also I'm really happy and grateful for this opportunity of the stay. And I hope to see you in the future. I'm going to leave on Sunday, so I hope there will be other occasions in the future to meet. Thank you very much for your attention.
So, thank you, Andrea. So, any question? Here.
Hi, thank you. Very interesting. So, this the connection of the sensors how expensive does this look like? Do you try every note?
Good question, very good question. In simulation, we can do everything, okay. When we tried other systems that are, let's say, that can be easily physically realized, we had to rely on some combinations for that, because otherwise it is expensive, yes. And so that's why the results I've presented, the initial ones were just on sensors to show the principle of the experiments, but actually we have to consider both the connections in the two cases, which extend the space that can be searched, and also the Boolean functions or the parameters of the system, which are much easier to be changed. But in fact, this is a technological limitation that for the moment might prevent obtaining complex behaviors. Yes.
Do you think criticality, so nowadays entropy is used as a regularizer often in artificial neural networks or reinforcement learning. Do you think criticality would be a better regularizer? Because I guess a critical system has a high entropy, but not the highest. And now we are aiming for the highest entropy, but maybe we should be aiming for criticality.
It depends on the goals. I think the point is that if you want to maximize the possibilities, then you look for maximal entropy in that. And criticality is a kind of balanced metric for the number of options that you can choose and the robustness of these options. We also try to evolve classifiers based on Boolean nets by letting the system decide how many classes to use. Okay, so the system was free to decide a class is an attractor, so it's easy to do that. But also what is important is that each attractor has a large enough basin of attraction. Otherwise, when you start from a condition, just a tiny change might end up in a different class. So in that respect, I think criticality can be useful if you don't have a given number of classes, but you still want reliable answers from the system that is subject to noise. I'm not aware of specific studies on that. So I cannot give you references on that. It might be, but it depends on the goals.
Other questions? So there is a question there.
Hello, Andrea.
Hello.
Hello, everyone. It's Thomas Velos here from the Center Leo Apostel research center that I don't know if you know it, but it has been around for a while. It's an interdisciplinary center at the VUB. And I'm sorry that there was a strike today, so some people could not come. I just got some messages. Yeah, I bike, so yeah. I want to give a small reflection and then a question. Because you end up saying about the responsibility that we have to acknowledge the features of criticality on our behavior, on our actions, especially working with robots, AI, all these, societal issues. But I want to look at the other way around, because if we are also part of these criticality processes, we have to acknowledge we are being influenced by many levels. So that gives another dimension of self-reflection of who we are. Not just what's our impact in the world, but also what are we made of. Maybe we are very ignorant of what are we made of. We might be part of very long transients, and our existence is part of that. So it's a sort of philosophical reflection that maybe contributes to that. And the second question is on the when you were saying what can we change, and we have this system made of perceptor, controller, and actuator. We can change the goal as well. So the goal is left out of the picture, and I think that this is, I'm open to discuss the fact that this might be a fundamental drawback of the architecture itself to describe systems, but thinking on robots and agents in the future, because biological entities have somehow these goals somehow embedded in the architecture. So we can only change nodes so far here to arrive to a goal or perform, but we cannot like modify the goal by the very architecture that is perceptor, controller, effector, which is coming from Rosen earlier than Kaufman. So I wonder if you have gone through this, like questioning the very goal configuration process within the architecture. Yeah, because there's probably criticality aspects for it as well.
Yeah, thanks for the comment and the question. You're right, but concerning the first observation, you are right, and this is and criticality is also a good way to know better ourselves. And concerning the question, we have made experiments with non-specific tasks. So going back to cybernetics, we want a system that survives. So the modeling from cybernetics and HP is that I don't care about the goals, your specific goals or task-oriented goals, but you just have to survive. So do what you can for surviving. And we made tests, but these robots are already artificial and they are simulated, but we did this with artificial agents, so even more simplified environments, in which basically the goal of the agent was to keep some essence variable in given ranges. So no goal was specified, and the interactions with the environment were abstract, so we didn't give meanings. Here we have proximity sensors, ground sensors in the examples I've mentioned and the results I've shown you, but in this case, in this study, it was just an interaction with a Boolean, critical Boolean word environment. And I have to admit, we were looking for criticality there, and there are mild signals that that critical systems work better, but they are not as strong as we expected. But still, with some interesting results. We have a paper published recently in Sensors about that. So you're right. Whenever we add explicitly a task function, it's something that we impose to the system, and it is somehow a simplification of the overall architecture of a model for a living system. Yes.
Okay, so there is a last question.
Okay, thank you. That's an honorable place for a question. Thank you, Andrea. I admire your didactic as well as your research capabilities. Fantastic. So it's a question more of a promotion. You probably know that the work of Gregory Chaitin, who, again, by argument of entropy, but algorithmic complexity rather than entropy, finds. Should I repeat everything? Okay, sorry. So it's amazing that these two are resonating so close by the work of Gregory Chaitin, another great man like Kaufman, who proposes that Darwinian evolution, is neither random nor ordered, but it has to be critical. And he has written a very small book, but very strong argument, proving Darwin, where he states, coming from a different direction, that of algorithmic complexity, he arrives at the same things like you.
I answer quickly because this would require a long discussion. But yeah, I'm aware of that work, and I like also the perspective from algorithms. in that sense. So very often Chaitin is just cited for the maximum complexity of a program and not for this part. Yeah. As you know, and several people here, I'm really influenced by the work by Kaufman, and so I cited him and his work. But there are other, of course, other who say maybe the same thing or a similar, reach a similar conclusion from different perspectives. Thank you.